Okay, today we're going to look at the polar coordinate system. So far, you have been representing graphs of equations as collection of points, x comma y, in the rectangular coordinate system, where x and y represent directed distance from the x or y axis respectively. In this lesson, we're going to be learning about a different system called the polar coordinate system. So we're going to learn a whole new way of graphing, which is the polar coordinate system. Okay, to form the polar coordinate system in a plane, you fix a point 0, or O, which is called the pole, and construct from O an initial ray that's called the polar axis. So I'm going to go down here. So this, where on the rectangular plane your origin's at, that's where your pole is on the polar axis. And your positive x-axis on your rectangular coordinate system is now your polar axis on this. So think about how we graph equations in standard form, angles in standard form. You know, a positive x-axis was our initial ray. That's the same thing here. Then each point P can be assigned a polar coordinate. Polar coordinates are in the order as an order pair r comma theta, where r is directed distance that O is from P. So the distance that O is from P, and positive means you're going in a positive direction, negative going in the opposite direction. And so in this case here, I'll put our point r theta. And so to figure out my radius, my r value, I would look and see I've gone in the positive direction from that pole, and I've gone 1, 2, 3, 4, 5 of those radius distance, those units distances. So r would be 5 in this case. So I can plot this point as phi comma theta. Now theta, let's figure out what that is. That is your directed angle. So what I mean by direction, it could be positive or negative, tells us which direction it's going. And that's, remember, just like in standard position, if we're going counterclockwise, or in a positive angle measurement, clockwise, or a negative angle measurement. And so this is approximately at pi over 4. So this dot I plot on this coordinate system would have the polar coordinates of 5 pi over 4. And that's what we're talking about when we're talking about from point P. All right, so let's practice plotting points that are in polar coordinates. So our first example here, we have the point 3 comma pi over 6. Now you always want to start by plotting your angle. So you're going to start with your polar axis, and then you're going to go, for a positive angle, you're going to go clockwise, pi over 6. So pi over 6 is about 30 degrees. So here's my pi over 6. There's my angle theta. So I've kind of graphed theta on this, which is pi over 6. And then from the pole, I'm going to count out 3 units. And then on that line, that's going to be the dot. So my point is this point I just plotted is at 3 comma pi over 6. So this point here is 3 pi comma pi over 6. Now, example B, I'm having you to deal with, we're directional. And now this time our radius is negative, and so it's going in the opposite direction. So let me explain how you would graph this type of point. Again, you're going to start with your theta. So our theta here is 7 pi over 6. So we're going to plot 7 pi over 6 angle in standard position on this polar coordinate system. Okay, so here is my theta. So I plotted angle theta, 7 pi over 6. Now, since my radius is negative 3, instead of going 3 in that direction, I'm going to extend this line in the opposite direction, and I'm going to count out 3 in the opposite direction. So 1, 2, 3, there is my dot. So this is the point, negative 3 comma 7 pi over 6. Now notice these 2 points, these 2 polar coordinates that we just did, A and B, are totally different points, but look, their ending value is at the same point, at the same spot on the graph. Interesting. Now I want you to try these 2. Let's start with this first one. Plot negative 6, 2 pi over 3. Okay, start by plotting your angle, 2 pi over 3. And then since our radius is negative, we're going to go in the opposite direction, 6. And then put a dot. So this is where your point negative 6 comma 2 pi over 3 should have ended up at in quadrant 4. So again, I'm going to start by plotting my angle theta, which is negative pi over 3. And then I'm going to count off on that ray 6 units. And this gives me my point 6 comma negative pi over 3. Oh, look, they end up being almost the same spot, or they are the same spot on our graph. Interesting. In fact, this is something that occurs quite often in polar coordinates because of, theta is, our trig functions are periodic. So in the rectangular coordinate system, x comma y always graphs a unique point. But as I just did in my last example, this is not true for the polar coordinates. Okay, we had a couple of points that were totally different, but yet they plotted the same values. Okay, in general, r comma theta can be plotted as you keep going around the unit circle as r comma theta plus or minus 2n pi. Or any point r comma theta can have the same coordinate with the opposite radius as long as you take theta plus a odd number of pi. So theta plus or minus 2n plus 1 times pi. Of course, n is an integer. All right, so let me illustrate this first one. Okay, so we got r comma theta. Let's say it's represented here in quadrant 2. Now, if I just took and went one more time around the unit circle, so that's theta plus 2n pi, or 2 pi, that would give me the same, it would end up at the exact same point. So that's what that one illustrates. An odd multiple of pi if you change your r to negative r. Okay, so this is the point r comma theta. Now, if I did opposite of r, that means that this ray needs to be extended out in the opposite direction. And it would end up over here. So if I started with theta and I added pi to do a straight line, and then instead of learning my r, I did my opposite of r, it would flip me back to that same point. Okay, last thing that's kind of important I want to talk about on your polar coordinate system is the PO, the order pair that represents the PO, which is 0 theta, or 0 with any angle measurement can go there, because you have that point, or your radius is 0, so it doesn't matter what your angle is. If your radius is 0, you're staying right there at the pole the whole time. Okay, let's practice finding multiple representations of each of these polar points. So we're going to find two additional polar representations for the point in between negative 2 pi and 2 pi. So first thing we're going to do is we're going to start by looking at our original given point. So this is negative 8 comma negative 5 pi over 2. So start with theta, and we're going to graph the angle negative 5 pi over 2, which ends up here. And then since we're doing negative 8, we're going to extend the line and go in the opposite direction on that ray. And we're going to end up here at negative 8 comma negative 5 pi over 2. Let's find a one that has the same radius. So we're going to keep the radius the same. And then as our rules that we just came, if I just add 2 pi, and I'm adding instead of subtracting this time because I want to stay between negative 2 pi and 2 pi. So adding 2 pi to negative 5 pi over 2 gives us negative pi over 2. So it gives us negative pi over 2, gives us down here for our quadrantial angle. And then I'm going to do a negative radius, so that's going to flip it up to at the same point. So yes, that one works. So negative 8 comma negative pi over 2. Now let's find one where the radius is the opposite. So we're going to do radius as 8 instead of negative 8. And when you do the opposite radius, you need to add or subtract odd multiples of pi. So I'm going to take negative 5 pi over 2 and I'm going to add pi. So 8 comma negative 3 pi over 2 is my order pair. So let's graph that. Negative 3 pi over 2 ends up here, and then a radius of 8 going this direction gives us the exact same point again. So yay, that worked. Okay, we'll start by plotting theta, which is 5 pi over 6. And we have a radius of 2, so it gives us a point here in quadrant 2. Now, if I'm going to keep the same radius, okay, I need to add or subtract 2 pi. Since I need to stay between negative 2 pi and positive 2 pi, I'm going to choose to subtract 2 pi this time. So I'm going to take my theta, which is 5 pi over 6, and subtract 2 pi. Finding a common denominator, I see that 5 pi over 6 minus 2 pi is equal to negative 7 pi over 6. So I'm going to graph the point negative 7 pi over 6 and then do the radius as 2. I want to do it in red. So there's our angle, negative 7 pi over 6 and a radius of 2. So yay, it worked. Okay, now let's find it with a radius that's negative 2. So if my radius is different, I'm going to take my theta, which is 5 pi over 6, and add or subtract pi. So again, to stay within negative 2 pi and positive 2 pi, I'm going to subtract pi this time. And that gives us a negative pi over 6. So I'm going to do this in purple. So I'm going to start by plotting my angle negative pi over 6. And then doing the radius of negative 2, which gives us right back to where we were at. And so that's our additional point. Now we can convert from a rectangular coordinate system to a polar coordinate system very easily and vice versa. So that's what we're going to learn next. And to do this, we're going to refer back to our right triangle trig, because any point that we plot on either of those axes is going to form a right triangle, where here is my opposite side, because I'm looking at my angle theta, which is my central angle, and I got my opposite, adjacent, hypotenuse. So remember, tangent is equal to opposite over adjacent, which is y over x, sine is equal to y over r, and cosine is equal to x over r. So that's just a review of right triangle trig. Now, if I want to convert from a polar coordinate to a rectangular coordinate, that means I know r and theta, and I want to find x and y. So we got to figure out an equation to represent x. So I'm going to go back to this cosine of theta is equal to x over r and solve this equation for x by multiplying each side by r. And so therefore, I have the equation x is equal to r times cosine theta. Now to find y, we'll do the very similar thing to our sine of theta is equal to y over r. Multiply each side by r, and I get that y is equal to r sine theta. So those are our two equations that we need to memorize to convert, if we're given r and theta, to convert to x and y. Now let's say I want to go in the other direction and convert to our rectangular coordinate system and make it polar. So I'm given x and y and I want to find r and theta. So r and theta is what I need to find. So the best thing that represents theta that has an x and y in it is this tangent. And so in order to solve for theta here, I need to take the inverse tangent or the arctangent of y over x. So theta is going to be equal to the arctangent of y over x. And then to find the only thing that represents x and y, if I do this right triangle over here, I remember my Pythagorean theorem, which is x squared plus y squared equals r squared. There I have r related to my x's and y's. So I'm going to use that formula. And so I can either use it as r squared is equal to x squared plus y squared, or if I want to get r by itself, I can square root each side, and I get that r is equal to the square root of x squared plus y squared. And so now I figured out, in terms of x and y is what I'm given, how to find r or theta. Now there is because again, each polar point can be represented by multiple angles. So to figure out your angle theta, you need to pay close attention to what quadrant the original rectangular point was plotted in. So let's say I had the rectangular point negative 2, 4. Well, negative 2, 4 is in quadrant 2. So when I find my angle theta, I need to find an angle in quadrant 2, but I have a problem. Recall that the inverse tangent only falls in from negative pi over 2 to pi over 2. So we're going to have to do a little bit of extra work to figure out that to get the right quadrant of theta. So that's the hardest part of these. So let me just kind of show you by example. So we're going to convert each of these points to rectangular. So I'm given that, recall that x is equal to r cosine theta. So r is 2, theta is 5 pi over 4. So I'm going to use my unit circle, and to figure out the cosine of 5 pi over 4 is equal to negative square root of 2 over 2. Multiplying that by 2, the 2's cancel out, and I just get negative square root of 2. To find my y coordinate in my rectangular system, I'm going to use the equation y is equal to r sine of theta, replacing 2 with r and theta with 5 pi over 4. Simplifying this down, I end up that y is also equal to negative square root of 2. So the corresponding rectangular point for this polar point is negative square root of 2, negative square root of 2. All right, so x is equal to negative 3 cosine of negative pi over 3. So that's going to be negative 3 times, for my unit circle, I know that cosine of negative pi over 3 is equal to 1/2. So x is equal to negative 3/2. Then to find my y, I'm going to use the equation y is equal to r sine of theta, where r is negative 3 and theta is negative pi over 3. Using my unit circle, I know that sine of negative pi over 3 is equal to negative the square root of 3 over 2. Multiplying this out and simplifying down, I get 3 the square root of 3 over 2. So my corresponding rectangular coordinates is negative 3/2, 3 square root of 3 over 2. Now let's try going in the other direction. Now this one is a little bit harder because you have to focus on which the quadrant theta needs to be in. So we're going to start with our rectangular point, negative 3, 4. So recall that r is equal to the square root of x squared plus y squared. So I can just substitute that in and find my r value very quickly. I get r is equal to the square root of 25, so r is equal to 5. Now I'm only going to use the positive value here. I'm not going to do the plus or minus because we know that graph's the same point.
Okay, so then I plot my original rectangular point, -3, 4, and figure out it's in quadrant 2. So I recall that, and for quadrant 2, tangent is going to be a negative value. And then when I do inverse tangent, remember that only gives me values between -pi/2 and pi/2. Now, if I'm in that quadrant 4, which is a negative value, that gives me the negative tangent values. So I know my answer is going to end up being in quadrant 4 there. And so in order to find this, I need to add pi to go across that straight line. So I'm actually, instead of typing in just my tangent that I did here, I need to do pi plus the inverse tangent of -4/3. Because for my calculator, that answer is going to be down here in -4. I need to be over here in quadrant 2. So the only way to get there is to add pi. So what I'm going to type into my calculator is pi plus the arc tangent of -4/3. When I type that in, I get 2.21. So my polar coordinates to this point is 5, 2.21 radians. So a little bit of extra thought finding the theta and going in this direction, since there's multiple representations of each. All right, I want you to try this next one. Okay, again, start with finding your r, so that all you have to do is plug in your x and your y into the equation r is equal to the square root of x squared plus y squared. Simplifying that down, I'm going to skip all that work, but you can show all your necessary work. I get that r is equal to square root of 13. Okay, so now we need to figure out theta. So first thing we got to do is identify which quadrant theta is in. So remember, theta is equal to the inverse tangent of y over x. And in this example, our original rectangular coordinate is in quadrant 3. So theta must end up in quadrant 3. But when we do inverse tangent, we don't get an option of quadrant 3. We get an option of quadrant 1 or quadrant 2. And so since tangent is positive in quadrant 3, when I do that inverse tangent, I'm going to get an answer in quadrant 1. So to get to where I want to go, I'm going to take that quadrant 1 angle and add pi to it, and that'll give me my correct answer. So theta is going to be equal to pi plus the inverse tangent of negative square root of 3 over -7, which I'll just drop the negatives and just kind of square root of 3 over 7. Type that into my calculator, I get 3.38. So my corresponding polar coordinate is 2 to the square root of 13, 3.38 radians. Now we know how to convert points from polar to rectangular and rectangular to polar. Let's convert equations. So to convert a rectangular equation to polar form, okay, we're going to use the same formulas we did with the coordinates. Recall that x is equal to r cosine of theta, and that y is equal to r sine of theta. And recall that x squared plus y squared is equal to r squared. So to convert to polar form, everywhere I see an x, I'm going to plug in r cosine theta. Everywhere I see a y, I'm going to plug in r sine theta. And then I'm going to simplify the equation. So I'm going to get rid of the parentheses by distributing the 3 and then distributing the 5. And then I'm going to move the 2 to the other side so I can factor out an r, because I only need one r, not two r's. And then I'm going to divide each side so I get r by itself. And so I get the equation r is equal to 2 divided by 3 cosine theta plus 5 sine theta. And that is my polar form of this equation. Okay, let me try another one that's a little bit more challenging. Again, the first way I'm going to start is I'm going to replace every x with r cosine theta and every y with r sine theta. Okay, now I'm going to get rid of the parentheses by distributing that square to each of the bases. So I get r squared cosine squared plus r squared sine squared. All of that still inside that outer parentheses of still squared. And then doing the same thing, distributing the square on the right-hand side. And then I'm going to factor out r squared from this inside portion. I get cosine squared plus sine squared. Now I did that because cosine squared plus sine squared is one of our Pythagorean identities. And so we're going to be using a lot of our trig identities here that we learned in our last unit. So I remember that sine squared plus cosine squared is equal to 1. So that left-hand side is just r squared squared, which is r to the 4th. And then on the right-hand side, I'm going to factor out our r squared. Again, I'm trying to get all my r's on one side. So I'm going to divide each side by r squared, and I end up with r squared is equal to cosine squared minus sine squared. Well, cosine squared minus sine squared is also an identity we have. That's a double angle formula, so that's equal to cosine of 2 theta. So we can stop there. R squared is equal to cosine of 2 theta. All right, you're going to try this your turn problem. So again, everywhere I see an x, I'm going to plug in r cosine theta. Everywhere I see a y, I'm going to plug in r sine theta. and I'm going to just simplify it down. So distributing that square root of our bases, I get r squared cosine squared theta plus r squared sine squared theta, and that's equal to 25. Factoring out my GCF of r squared on the left-hand side, I get r squared times cosine squared plus sine squared is equal to 25. Well, again, Pythagorean theorem, r squared plus cosine squared is equal to 1. So I get r squared is equal to 25, or r is equal to 5. So equation of a circle in polar form is just r equals a number. Interesting. All right, now let's talk about going in the other direction. Now we're going to convert from polar to rectangular form. So again, want to recall some of those formulas that we used with the polar coordinates. When we did polar to rectangular coordinates, r squared is equal to x squared plus y squared, r cosine theta is equal to r x, r sine theta is equal to r y, and tangent of theta is equal to y over x. So here I'm given r is equal to 4. So I can replace r with square root of x squared plus y squared. Square each side, I get x squared plus y squared is equal to 16. And there's my equation. Now I have a problem on B because, again, in order to substitute in place of x, I need r cosine theta, but all I have is 3 cosine theta. So in order to get the r, I'm going to take that denominator of 3 cosine theta minus 4 sine theta and multiply it on each side of the equation to get r times that is equal to 7. Now distributing my r and getting rid of the parentheses on the left-hand side, I'm going to end up with 3r cosine theta minus 4r sine theta is equal to 7. Now I can replace that r cosine theta with x to get 3x minus, replace the r sine theta with y to get negative 4y, or minus 4y is equal to 7. And so there is my equation. Okay, you try this last example. First thing I notice is I have to replace that double angle formula because all our equations have just sine theta and cosine theta, nothing with double angle. So I'm going to replace sine of 2 theta with 2 sine theta cosine theta. Then I don't have any r's on the left-hand side, so I'm going to square each side. I'm going to multiply each side of the equation by r squared. So I get r to the 4th is equal to r squared times 2 sine theta cosine theta. Now I'm going to distribute that r, break it up, and put one r with a sine and one r with a cosine to write it as 2r sine theta times r cosine theta. And so now I have an r sine theta that I can make a y, and an r cosine theta I can make an x. So on the right-hand side, I have 2yx. Now let's get rid of the r on the left-hand side. So again, r to the 4th is the same as r squared quantity squared. So I can replace that with x squared plus y squared quantity squared is equal to 2xy. Now you do not have to distribute, you do not have to multiply x squared plus y squared times x squared plus y squared. All you do is get it equal to 0, and this is a legit answer for this problem. Okay, hopefully this has been a good introduction to the polar coordinate system. See you later.